Sophia Landis, and I'm going to talk about the outcomes and the findings of our constant velocity lab. So, the basic principles and purpose of this lab is to investigate an object moving at a constant velocity and how that ties into these basic physics principles. So, first we have Newton's first law, which is every object will remain at rest in a uniform motion in a straight line unless an external force acts against it. So, an object should remain at a constant velocity unless there's a force acting on it, which is what we should observe. Newton's second law, which says that force equals mass times acceleration. So, if there's no acceleration, there should be no force. And if there's no force, there should be no acceleration. So, then an object should not accelerate unless that force is applied to it. And so these principles can kind of be seen in this velocity and position formula, where velocity is not going to change unless the net force is not zero. So as you can see, if the net force is zero, this is going to be zeroed out, and velocity initial is going to equal velocity final. And so the same kind of happens to position, where position's changing according to velocity. So if velocity is not changing, then position's only going to change at a constant rate. So what are the models we used to investigate this? We used a practical demonstration of a video of a piece of tape rolling. The system in this practical demonstration is this little roll of tape, and the surroundings is just everything else. The table that the tape is on, the earth that the table's on, everything else surrounding this little roll of tape. And you can see that our position graph is a kind of straight line, so it's kind of changing at a decently constant rate, but there's a slight curve into it because of some error, which we'll discuss later. And then our theoretical demonstration, which can be seen here, it's a perfectly straight line because velocity is held constant, so it's changing at a constant rate. And so our results is this graph, which we have our actual velocity or our actual position versus time graph with our theoretical one, and both are decently straight lines, which demonstrate the principle that there should be no force acting on it, so velocity should be held constant, so position should be changing at the constant rate because velocity is constant, and velocity is the rate at which position changes. So what is the process that we use to get these models? We had the practical demonstration of the roll of tape. So we videoed a piece of tape rolling on a track, or a roll of tape rolling on a track. We put this video into a tracker application and used that application to get data to put in into an Excel spreadsheet to get the charts that we used earlier. In the theoretical demo, we had code, so obviously a little more complicated. We had to initialize our initial conditions. Then we had to use some iteration to kind of show that update of velocity and position. So here is kind of the most important piece of the code, the velocity and the position updating. So net force is zero, so velocity isn't updating, so velocity just stays the same, but position does change because there is a velocity, so position is going to change at a constant rate. So what are the what ifs? What can we gather from all of this information? Well, we can kind of see how maybe flipping the x axis could kind of affect our change in position over time and our velocity. So obviously now velocity is positive because position change is increasing over time. If I made it so that instead of right moving left is negative, moving left is positive. So it's going to make it positive velocity, and our position is going to increase instead of decrease. And so what does all of this mean? Let's put it all together. So our glow script model works because the net force is zero. Why? Why is the velocity held constant? Well, we can see it demonstrated in our velocity update formula, where if net force is zero, then velocity final is going to equal velocity initial. It's not going to change. And so why is net force zero? It's because all the forces acting on object A cancel out. So theoretically, the forces acting the summation of all the forces, the net force, should equal zero, which you can see here. But in our practical demonstration, that wasn't the case. We had a slight imperfectly straight line for the position. So why? Obviously, the forces didn't perfectly cancel out. The summation of the forces didn't perfectly cancel out, so there was some error, but But we can see with our theoretical that if there's no forces, if there's truly a net force of 0, you're going to get that constant change in your position. And so that's what we observed. Thank you.